So, decision maths. We are on to topic 3, which is awesome news. And the even more awesome news is that maths is actually quite practical, and we get to see that side of it in this topic. We've already made it to topic 3, so awesome. Good work, everybody. We've made great progress today. So, for example, when we talked a little bit about I talked a little bit earlier about when I talked about the shortest weight or the shortest path, I talked about how we wanted to find like the most efficient route. So we're going to be exploring some more techniques and questions and things like that, and a few other things as well when we're talking about decision maths. So we could be talking about like the most efficient way to do a project. We could be talking about like maximizing traffic flow, finding the most efficient plumbing solution. There's all of these different things we can do. So we're going to have a look at it now. So we're going to introduce another definition. We're going to talk about another type of graph. And these special type of graph are called trees. So what is a tree? A tree is a connected graph in which we have no cycles. So this means we have no loops, no multiple edges. It must be planar, so it can only have one face. And trees will always have n-1 edges. So I feel like trees kind of look like spiky, like scarecrows or skeletons. Or you can almost think of it like a tree without its leaves. Like it's the bare minimum, most simplest graph where every vertex is connected, because trees must be a connected graph. And we also want no cycles, which means we can't have multiple edges, we can't have loops, it must be planar, and it can only have one face, because as soon as we added another edge there, that would actually introduce the presence of a cycle, and that would also mean we have two faces, so it would no longer be a tree. And because of this, we can also always know that trees are always going to have n-1 edges, which can be very handy to know. And we can see I've got a few more examples here. It could look like that, or it could look like that. Trees can look like different things as long as they hold to these definitions. But what about a spanning tree? So a tree does not need to include every vertex of the graph. It just has to be connected with no cycles and no loops, no multiple edges, all of that. So a spanning tree of a graph is a subgraph, which we talked about earlier, that is a tree involving every vertex. So a subgraph, so some information removed but nothing added, but it does need every vertex. So a spanning tree means that some edges have been removed. And then to make our definition a little bit more specific, a minimum spanning tree is the spanning tree of a weighted graph with the total minimum weight. So we're coming back in a little bit more to what I mentioned earlier with almost like the shortest path, except here we're not talking about like path. We're talking about the minimum spanning tree, which is the spanning tree of a weighted graph with the total minimum weight. So we want to connect every edge in, we want to connect every vertex in with the absolute minimal number of edges, so with no loops, no cycles, no multiple edges, so that we can get the total minimum weight, so that we can have the most effective project, road, plumbing project, whatever it is our graph is representing. And some can actually have multiple different minimum spanning trees. There could be a few different solutions that could help us get the total minimum weight. So that's important to keep in mind as well. And how do we find the minimum spanning tree? We do it using Prim's algorithm, which when you think it through is actually a very, very logical process. So what you do to do Prim's algorithm and find the minimum spanning tree of your tree or your graph, you pick a vertex. You can be any. You can literally pick any vertex and Prim's algorithm will work, and that'll be your starting point. And then you select the edge connected to that vertex with the smallest possible weight. And then so now you've added in another vertex and you'll have one edge connecting those two vertices. And that edge will have the smallest possible weight. And then now what you're going to do is move around the rest of the graph, connecting in every single vertex by using the smallest possible weight. So you keep adding edge after edge with the smallest possible weight. So you add another edge that's connected to one of the vertices that's already in your graph and also has the smallest weight. So every time you're connecting in a new vertex, but adding the minimum weighted edge, and that doesn't introduce a cycle. Because if the minimum weighted edge introduced a cycle, well, we could add it, but that wouldn't actually help us or serve a useful purpose, because it wouldn't be part of the minimum spanning tree because it would introduce a cycle. And then simply continue until every vertex is connected. So connector problems are all about finding minimum spanning trees. So for example, what's like the most efficient way to connect a group of towns by highways or like roads or trains? It could be about finding the minimum spanning tree to find the most effective way to do an electrical wiring setup in a house. Or it might be about solving a plumbing problem, because again, the goal is to find the total minimum weight. So it might help us find like the most cost-effective way to solve a problem. Or like connect towns in the cheapest way possible with different roads. So these are all like different problems they can help us solve. So let's have a look. So this graph here represents possible roads that could be built to connect various towns. So here, our vertices are different towns in a certain area, and our edges are possible roads that could be built to connect the towns, and the weights or the numbers associated with the edges represent the number of kilometers apart that the towns are. So the question is asking us is, what is the smallest length in roads possible to have all the towns connected? Is the minimum spanning tree going to have a total weight of 55, 56, 58 or 59 kilometers? Let's apply Prim's algorithm. So what I'm going to do is I'm going to start with the vertex in the bottom left-hand corner. And I'm going to see that I've got two edges attached to it, one with a weight of 2 kilometers and one with a weight of 3 kilometers. The most effective, the most minimum cost-effective way to connect in this vertex is by building that road there. So we're applying Prim's algorithm. Okay, so now my graph has two vertices, like the Prim's algorithm step said that it would. So now I've got to find the next most efficient way to add in another vertex. If I added this one, it'd give us a weight of 5. This one would give us a weight of 5, but connecting in this one would give us a weight of 3. So I'm going to choose to add in that one there. Awesome. Now I've got 3 vertices in my tree. All right, to add in another connection, I could add this, which is a weight of 10. Not ideal. Weight of 7, still a lot. Or we have the options of 5 or 5. And out of those options, 5 is definitely the lowest weight. So we're going to add in one of the 5s. And because they are the same weight, it doesn't matter which 5 we add in. So I'm going to choose to add in that one. And then I'm going to continue doing this exact same process, moving around my whole graph. So I can see that every edge connected to all of these, the next lowest weight would be this one here, connecting in that vertex because it has a weight of 3. Next, I'm going to connect in the vertex next to it by that root of 4. And then this is where we come to a bit of an interesting decision. If I look at everything connected to all of these different things that I've got in my graph so far, I can see that my lowest weights are 5. And before I said earlier we could connect in either 5 because they were the same weight. But even if this weight here was a lot lower, there would be no use adding this one here because it would add a cycle. So it would no longer be a tree, and it also is completely unnecessary because both of these vertices are already connected into our graph. So I actually don't even need to worry about building that road because we're trying to build these roads the most cost-effective way possible. So if I want to get to this town from this town, all I have to do is go that way. It would definitely be more efficient to have a road there, but it's cheaper to only build the minimum amount of roads. So that's the goal of this project. So the next thing I'm going to do is add that center vertex by that road of 5. And then I'm going to keep moving around my graph by using the same process. My next lowest weight is 6 by that one there, that connection. Then my next lowest weight will be that one there. And then as I keep adding them, if you want to pause or slow down the video to see the order that I've done it in and the thought process behind each connection, you totally can. But that is the process that I undertook. So what we do next is we add the weights of the edges in our minimum spanning tree to find the minimum weight in kilometres that's required to connect all the towns. And the answer is 59 kilometres. And if I actually take away the picture from behind our minimum spanning tree, it actually gets even clearer. Like, that is so clearly a tree, because you can see we have no cycles, no loops, no multiple edges. It literally looks like that skeleton, or like that dead tree with no leaves. It's the bare minimum number of connections between all of our towns with the lowest minimum weight. So the most effective, most cost efficient, easy possible way we can connect all the towns is by having to build 59 kilometres of road. And to check our answer, we can also use the equation to make sure we added the right number of edges. So number of edges in the minimum spanning tree, number of vertices take 1. We have 17 vertices and I've added 16 edges, so we can tick that off. We know that we've done it right. So that's an example of using Prim's algorithm to find a minimum spanning tree and solving a connector problem, because we've found the most efficient way to connect all of our towns here. So which of the following represents a tree? A graph with 14 edges, 5 vertices, 12 edges and 10 vertices, 6 edges and 7 vertices, or a graph with 11 and 11? So C, we can actually see, is correct if we use that little rule that we talked about earlier, because we said that a tree of n vertices will always need n take 1 edges, because that's the number of edges required to connect in every vertex without introducing loops, multiple edges or cycles. So by using that formula, we can solve a question like this one here. And I could draw that to illustrate it. And again, it could be any type of equivalent graph, and it would illustrate the point I'm trying to make. So we can see here our graph has 6 vertices, 1, 2, 3, 4, 5, 6. 7 vertices, 1, 2, 3, 4, 5, 6, 7 vertices, and we have 6 edges connecting them all. So we can see 1, 2, 3, 4, 5, 6, and we can see that that's a tree. But as soon as you introduce an extra edge, it actually no longer becomes a tree, because we've introduced a cycle. So we can see here, even by visually drawing it, not that we need to, that that is our correct answer.